All right, so next we're going to talk about the parametric equations for a straight line. Okay, so let's imagine an object moving at a constant speed. Okay, so the um, the x component of velocity we're just going to call a. So it's a constant value. Same way with a y value. It's just a constant value of b. Okay, so we're moving at constant speed, and we're going to pass through this point x0, y0. Okay, that's sort of like our initial position at t equals 0. And so if an object is moving, or some particle, a lot of times this book uses particle, refers to particles moving along things, along curves. In this case, it's a straight line. So if you imagine this particle moving from, say, here's x0 comma y0, right? And then over 1 unit of time, it's going to move a in the x direction and b in the y direction. So this next value will be x0 plus a and x0 plus b, okay, over 1 unit of time. So this would be at t equals 1 if this is t equals 0. All right, so the equation of the line then will just be the initial position plus that velocity or that speed times the time, because we're just moving at a nice constant speed. Okay, so we can just take the initial position x0 and y0 and add the speed, right? This speed times time, right? The rate times time to get any other point on that line. Okay, and the slope of the line, dy dx, is essentially dy dt over dx dt. You can see how like these dt's, these differential changes in infinitesimal changes in time cancel out effectively, and so the slope of the line will be b over a. Okay, so the velocity in the y direction over the velocity in the x direction. All right, that's a lot of that's a lot of real general information. Let's look at an example, and I think it'll make more sense. So in example 3, we've got a line that's passing through these 2 points, A and B. A is 2 comma negative 1, and B is negative 1 comma 5. And we want to find a set of parametric equations for this line. So let's just take a look at it. I'm just going to quickly graph what that looks like. Okay, so we have 2 comma negative 1, so that's about here, and then negative 1 comma 1, 2, 3, 4, 5, so something like that. All right, so we're moving along this line. Okay, and so we're asked to find a set of parametric equations for this line, assuming that a particle is moving from A, so this is point A and this is point B. We're moving from point A to point B in 1 unit of time. Okay, so if that's the case, then our change in x over change in y, our dy d, or sorry, dx dt, right? Our change in x with respect to time is just going to be our change in, again, we're dealing with constant speed, so we have it. We can take the change in x over 1 unit of time, right? And our change in x, right, is just we're going from 2 to negative 1. Right, so we're basically in the x direction, we're going down by 3, right? So, or we could get that by taking y2 minus, or sorry, x2 minus x1. So we could have negative 1 minus 2 over 1, right? So our dx dt is just going to be minus 3, right? That's our change in x over 1 unit of time. And then we can find the velocity in the y direction, dy dt, right? That's just going to be our change in y over time, right? And we're assuming it's moving from A to B in 1 unit of time. And to go from A to B, we're going from -1 to +5. So we're going up by 6. Okay, or you could think of it as 5 minus a -1 over 1 unit of time. Okay, and that gives us 6. So we can write the parametric equations for this line by taking x. We're going to take the initial position 2, and it's moving by 3 units in the negative direction for each unit of time. Okay, and then the y value, we'll just take the initial position of -1, and it's moving by a positive 6 units for every unit of time. Okay. Now you can always test this, make sure you've got it. If I put in 0, obviously then I get 2, -1. So I'm starting out at t equals 0 at A. And if I put in t equals 1, I want to get the B value, right? So if I put in t equals 1, I'll get 2 minus 3, which gives me the x value that I'm expecting at B. And if I put in t equals 1 into the y equation, I get -1 plus 6, which gives me positive 5, which is the y value that I want for the point B. So you can see that it works out for the points A and B. It does indeed move from point A to point B in 1 unit of time. Okay, so there's always a way you can check it. All right, so now the second part of this question asks us to find the Cartesian equation for the line. By eliminating a parameter. I think I maybe have some typo here. Let's see. Cartesian equation for the line by eliminating a parameter. I don't know what that is. I gotta edit it, I guess. All right. So okay, so we're just gonna take our parametric equations for the line, okay, and we're going to rewrite them. We're gonna try and rewrite them so that we have an explicit equation for y in terms of x. Okay, and we're gonna do that just by rearranging. We'll start by rearranging the x equation and solving for t. Okay, so I'm gonna get x minus 2 equals minus 3t. So I'm just taking that x equation and rearranging it. And so then I can get an equation for t. It's going to be x minus 2 over -3. Okay. Now I can take that expression for t and plug it into the y equation. So I'm going to get y is equal to -1 plus 6 times x minus 2 over -3. Now I'm going to cancel, let's see, I can cancel this and make it a 2, but I got to remember that it's going to be -2. So let's simplify this. I'm going to get -2, I'll multiply everything by -2, plus 4. Oh, and then I have this -1 here. I'm sorry, this is -2x. All right, I'm just distributing the -2. I canceled the I divided 6 by -3, got -2, and then I'm distributing the -2. All right, so and then if I make this a little simpler, I get y is equal to -2x plus 3. Okay, so there's a Cartesian equation for this line. All right, so we have the parametric equations, we have the set of equations for x and y in terms of t, and now we have an explicit Cartesian equation for the line and for an equation for y in terms of x. Okay. All right. So now the interesting thing is that this is not the only set of parametric equations that you can write for this line, right? It all depends on how this particle is moving along the line. So we could write different set of parametric equations for this line if we just assume that the particle is moving in a different way along the line. So in this, in part C, what we want is an equation, a parametric equation for the line, but we want to assume that the particle moves from B to A, right? So we're moving in the opposite direction, and we're moving in 2 units of time instead of 1 unit of time, okay? So remember, let's see, I'm going to scroll back up just so I can see the point. So B, I'm just going to write it down here. So B is -1, 5, and A is 2, -1. Okay, and then I can scroll back up and have some room to write. All right, so in this case, the dx dt, okay, we're moving from B to A, so our delta x is going to be, so well, delta x over now 2 units of time, and our delta x is now we're going from -1 to 2, okay, so we're going up by 3 in 2 units of time. All right, so so our dx dt is going to be 3/2. And then dy dt, again, it's going to be delta y over 2. And in this case, we're moving from 5 to -1. So we're moving in the negative direction by 6 over 2 units of time. So we get -3. All right, so that is going to give us a different set of parametric equations, right? So here we're going to start at -1 in the for x, right? And we're going to move by 3/2 each unit of time. So we're just going to add 3/2 t to it to get the next point in the x direction, in the next point in time. All right, and so the y value, because we're starting at B now, so we're starting at a y value of 5, and we are, oops, we're not adding anything. We're going to subtract. We're going to subtract 3t because we're moving 6 units. We're moving in the -6 direction over 2 units of time, right? So each unit of time we're moving in by 3 units in the negative direction, in the negative y direction. Okay, so here are the parametric equations for that same line. Okay, the only difference is that we're assuming a different motion of the particle along the line. Okay, but this represents the same line, and we can prove that by doing part D, which is to take these parametric equations we just figured out, and in part C, and write the Cartesian coordinates, or the Cartesian equation. Okay, so I'm going to take the x, the parametric equation for x, and I'm going to solve for t. So if I rearrange this and solve it for t, I'm going to get, I basically get x plus 1, and then I'm going to divide by 3/2, which becomes 2/3. Okay, so t is 2/3 x plus 1. And if I put that into my equation for y, I get y is equal to 5 minus 3, right, times 2/3 x plus 1. Right, I'm just substituting t into that equation. And then I can simplify it. I get y is equal to, I get 5, and then if I take -3 times 2/3, I'm going to get -2x plus 1, which gives me, I'm going to have minus 2x minus 2 plus 5, so plus 3. Okay, so I have my final equation. Let me write it out here, just so it's a little more clear. Y is equal to minus 2x plus 3. Now notice that is the same as part B. I got the same line. I've got the same Cartesian equation for the line, so it's the same line. It's just that the particle's moving differently. So this is the same as part B, which is good. That's what we want. right? It's the same line, so it makes sense that it would be the same. All right, and then finally, let's see, we're asked to find the Cartesian equation for the line using the point-slope form. Now, we were given 2 points, right? We were given the points. Let me write them down again because they're off the screen. So 2 comma negative 1 and negative 1 comma 5. Now, you know how to find the equation of a line between 2 points, right? We were just going to find the slope between those 2 points. Right, so I can say that the change in y is 5 minus a negative 1 over the change in x, which is negative 1 minus 2. So that gives me 6 over negative 3, which is negative 2. So the slope is negative 2 just based on those 2 points. And now I can use the point slope form of a line. So I get y minus, I'm just going to use this first point. So I'm going to have y minus a minus 1, which is y plus 1 is equal to slope, m, minus 2 times x minus the x value. In this case is 2, if I use that first point. And now it's just a matter of rearranging it. So I'm going to get y is equal to negative 2, and then I'm going to have negative 2x, sorry. So negative 2x plus 4 minus 1, so it becomes plus 3. So again, I got the same Cartesian equation for this line, right? So I did it 3 different ways. I used the good old point-slope formula, and then I also eliminated the parameter of the 2 parametric equations that we got for this line. So hopefully that makes more sense to you, and I think I have a problem for you to try out similar to this. So try this problem and then come back and I will go through it with you if you need me to.